Okay, now this is central to setting up integrals, even integrals in one dimension. You have to think in terms of partitions, okay? Because what the partition does is, again, for any point within this region, it lies within some x interval, subinterval down here, right? And some y subinterval. So if the mesh of this interval is fine enough, if we make all the intervals really tiny, in this direction and in this direction, then any point we choose here is going to be very, very close to our sample point. Okay? To the sample point in the interval within which this point lies. Okay? There's a grid. You know, this partition and this partition form something very much like a grid. Okay? Not all the grid lines line up in this direction because we're allowing the y partition to be for one x interval to be independent of the y partition for the next one by putting these eyes on everything. Okay? Does that halfway make sense?
About halfway, yeah.
Yeah, well, you've got to ponder it. Okay, so what we now do is we say, okay, let's go back to 3 dimensions.
Then we have another interval.
No, we just have to figure out what to integrate, although we already know. Okay? So back in 3 dimensions, and this is getting scattered all over the board, so maybe I better just put in another board here, okay? Back in 3 dimensions, let me go up kind of big. Okay? We have our region. Okay? We have a point within our region. Okay? And this point, for some ij, pick any I less than or equal to n, and any j less than or equal to m sub I. Okay? Now, n is a number of subintervals in the x direction. For a given ith subinterval, m sub I is a number of intervals in your partition of the resulting y interval, right? So, for any j less than or equal to m sub I, we have a rectangle x sub I minus 1 less than or equal to x less than or equal to x sub I, and y I j minus 1 less than or equal to y less than or equal to y I j. With the point xi star y I j star. Okay? So let's just say that here is that rectangle. Now I use green to indicate I'm just going to make the whole thing green. I'm not going to worry about that. Okay, so there's our region. Okay? So this again is xi minus 1 less than or equal to x less than or equal to x I y I j minus 1 less than or equal to y less than or equal to y j. yi. Okay? Now, what's the area of that rectangle? Well, what's its length in the x direction?
Is it 1? Or
I've partitioned this thing into 10 billion little sub-intervals. I've just exaggerated the
2x of 1.
size.
Sorry, yeah, x of 1.
You got it. What, say again?
It's equal to x of 1.
No, no. 1 would only be on interval number 1. And that interval would bound
X of I minus x of 1. Then?
no,
X of I minus 1.
x of I minus 1, x sub I minus 1.
Yes.
Well, x sub I minus 1 is the distance from here to wherever your x sub I is. It's a big distance, right? And this is a little tiny interval.
so it's x sub I minus x sub I minus 1?
Yeah, it's the width of this interval. If the x goes from here to here, then that's how, the difference of these is how wide the interval is, right?
Okay. I just got confused with your notation. Yeah.
Yeah, well, see the notation, I'm not sure. Using Stewart, right? Stewart's text. That explains a lot. Okay. Stewart's a great text. It's really well written, but it's not as rigorous as I would like.
That's what we used for Calc 1 and 2.
That's what I mean. Okay? I was thinking Stewart did that, but regardless, you got to know this. Okay? So the area is what?
X sub I.
I'm going to call it delta x sub I times delta y sub I j. Okay? And down here I'll just say that delta x sub I is just the width of this interval. It just goes from here to here, so it's this minus this. And your delta y sub ij, hope I've got room for all the subscripts. I'll kind of start it over here. Delta y ij equals, yeah, I'll make it yij minus yij minus 1, right? Okay? So that now I can just abbreviate the area like this, okay? And instead of writing out these differences, I'll just write delta xi and delta yij, because we know what they mean, okay? Well, that's the area. Now, that's the basic. Now we're going all the way up to our curve up here, right? Okay, so how high do we have to go? We can make a little parallelepiped in this thing, can't we?
We can't draw it very nicely.
No, I
But
can draw it really nice. You just watch me draw
Okay.
this, okay? There and there, because you know it doesn't have room to go up very much, does it? Or down. Oops, got a little crooked there, but here's our parallelepiped, right? It's got a little slope up here, maybe a little slope there, and slope here ought to be the same. But, okay, there we got our parallelepiped. How high is it?
the 2 square roots of
Okay. Well, the average height is taken to be what?
2.
F evaluated at the sample point. It's an I. Okay?
I forgot about the sample point.
You can't forget about the sample point because that's where you evaluate everything. Of course you don't know that. Okay? But now you do. Okay?
So the sample points are some infinitesimally, or some value.
The sample point is anywhere at all inside of this rectangle, but the rectangle is so tiny that what you get at one point is so close to what you get at any other point that it doesn't matter. And when you take the limit, as your delta x's and delta y's all approach 0, it makes no difference at all, and that's what your integral is. Okay? Well, yeah, I skipped a little bit in that statement, but we'll get to it. All right? So what's the volume? Write down the expression for the volume of that parallelepiped.